What's going on for the secant lines to approach the tangent lines? The distance in the points is becoming, and how do we show the distance between the points? You were right with the h as long as you make h delta x. So are you going to have some definition of derivative stuff? Yeah. Tell me one version. There's technically 3 that I need you to know this year. Wait. Limit as? Of? Okay. I want 2 different variations and neither of them to have an h. What's another one? Hold on. Limit as? X approaches a. Okay. Of? We could do that if you do it properly. You could do it either way, technically. Right? Because it would be f of a minus f of a. It's technically right. Usually it's f of x minus f of a. If you guys were, yeah. Ooh. Yeah. Whichever way you go, just go the same direction. So either f of x minus f of a all over x minus a, or f of a minus f of x all over a minus x. One more variation. Wait, hold on. Wouldn't this be f prime of what? Good. What's the last one? Anybody remember? Yeah. Well, delta x, hold on, so that'd be delta x approaching 0 again, right? So f of, keep going, Isa, a plus, good. Got it. Whoo, look at that guy go. Good. Why do I need you to have those memorized? Because I need you to recognize them in problems that are given to you for being what they truly are. Derivatives. Either general or particular. So, explain to me how this first one relates to the idea of the slope of the tangent line. The first one. How does it relate to tangent lines? Close. These two are a slope of a tangent line to f of x at. These ones give a slope or the slope of a tangent line or the tangent line, but not the first one. Aryan.
Okay, so I think it says delta x is like the change in like distance. It's saying like f of x is the one point, and then f of x plus delta x is the second one. And so since delta x distance is equal to r, so the points are getting closer to each other, which is how you get the.
Highlight everything except for the last 3 words, which is how you get not the tangent line. But yes, excellent. In the sense of we have 2 points, 2 generally noted in the have a position, a removed position to 0. So we have secant lines approaching tangent lines. But as soon as Aryan like, which I forget if you said shows or signifies or finds the tangent line, that's wrong. Why is it wrong? Kathy.
Well, wouldn't it technically be an equation that gives you the slope at certain points of the original function?
Yes. Do you see the difference? This one gives me a slope at a point, the slope at a point. This one gives me no one particular slope, right? Unless it would give me one particular slope if the derivative was a constant. But if the derivative is any formula, wouldn't this give me the function of all the possible slopes, right? Not just the slope, but all slopes. All slopes to the function f of x at all possible x values in the domain. that make sense? Okay. So difference between the derivative function and a specific derivative value. So the slope versus all slopes. Good, good, good? Let me dual page it just in case. I know some of you like to write exactly what I write. Not that it's that magical, it really isn't, but thank you anyway. Problem solving clues. So let's recap. Look, just in case we didn't get it from the last section. This one's pretty easy. F prime of A. I already showed it on the page before. Finding the tangent line. Remind me from the forever card. Bless you. Y minus the actual line. Y minus F of A equals. Yeah, at a point A, F of A, find the particular slope, F prime of A. What is, you guys help me from your entire year of practice, knowledge, from Calculus AB, what's the most common mistake I am going to see when kids are needing to find the tangent line? And no, it's not messing up the derivative. Not distributing, because you don't always have to stick it to the, you don't always have to simplify. Not really.
Oh, wait, is it the sign?
Nope.
Plugging in X to find Y.
Maybe. That's a common mistake, is if you have the X, they just kind of get lost, the disconnect of finding the Y. That's one. That's not the most common, though. Some of you made this mistake last year. Where?
Like in the X minus A, they just plug in that.
No. No, it's a good thought. It's right here. It's not solving for the derivative. It's almost, not almost never, but it's rarely solving for the derivative. It's not plugging in A. You know how many times people put the derivative like 2x or 3x minus 1 or 5x squared plus 1 right here? This isn't the place for an equation. What is this the place for? A constant, the slope at the point. So when I was making the distinction back here between the general derivative that gives all the different slopes at all the different points and a specific derivative, the most common mistake in Calculus AB when first starting with tangent lines or even later on in the year is putting a general derivative here when we need the specific slope. Does that make sense? Cool. So how are we going to find a normal line? Still a line, right? But what's different? Perpendicular. Negative 1 over F prime of A. Good. Normal to a curve, we'd have to find the tangent line first, aka the slope of the tangent line, I should say first, and then opposite reciprocal, and we're good. We're good to go. Whoo! Okay. It looks rough, but is it really that bad? No, but let me zoom in. Ooh, can I leave the page before? Okay, a couple more seconds, I'm sorry. Differentiability and continuity. Why am I putting this up? Section 3.1. Because I've joined 3.1 and 3.2, right? Section 3.1 was definition of derivative. Section 3.2, which includes definition of the derivative, notation, relationship between f and f prime. Oh, that'll be fun. Graphing the derivative from data, one-sided derivatives. 3.2 is differentiability. When will f prime of A fail to exist? Differentiability implies local linearity. Numerical derivatives on a calculator. Ooh, how do we take derivatives on a calculator? Isn't there something under math? The n derived one? And then there's the ddx shortcut, which is, isn't that the alpha y equals? Or on a graph, you can also use second trace. That calc menu has a dy dx, I think. An intermediate value theorem for derivatives. Ooh, there might be some interesting things that show up. It's really just definition of derivative and differentiability, but let's talk about what we saw last year as the most important takeaways for differentiability. What does differentiability even mean? Yeah, a function that is able to be derived. And it's like continuity, where everything could be good. It could be continuous everywhere but a point. It could be differentiable everywhere but a point. So what are the things that we need to look out for graphically? Sharp points and vertical tangents. But didn't we just recently talk about sharp points and vertical tangents? Kind of at length, like in a homework assignment? So let me zoom in and let's talk about those and get it actually in our notes and not just have it be a random conversation one day. So like in 3 months I can be like, oh hey, look at your notes, not just, remember that one time we talked about? Okay, so vertical tangents. I want to see more. My example got all messed up. There we go. Okay. If I was to take the derivative of something and have it equal 1 over 2 square root of x. First of all, be amazing, cool kids, just because we need to keep you guys sharp. Where could this one have come from? What could f of x have been? X to the 1/2, just square root of x. Double check. X to the 1/2 power, bring down the 1/2, negative 1/2. Got it. What's the domain of the original function? Greater than or equal to 0. Good. Okay. But as soon as you take the derivative, who is no longer allowed? That used to be allowed. So we have a point of this guy who is no longer I shouldn't say who is no longer, whose derivative does not exist. So how can there be a point of an original and have the derivative not exist? What's going on with the square root of x, guys? Why does it have a vertical tangent, though? You can think of it as a sharp point, but is it truly? No, it doesn't really have like another side coming in. It's a vertical tangent because when you come in, what happens to your slopes is you get an inch closer and closer and closer and closer and closer and closer. Yeah, the slope is going undefined because the slope is going infinite. So that would be an example of a vertical tangent line. Now how can I tell that? What's going on at 0? And Justin, what's going on if I have any number over 0? My derivative is infinity and beyond. See how you can see a vertical tangent? But what we see in homework technically that we have to be careful of when a function technically can come towards something from 2. This one doesn't. This one only comes from one side, so I don't have to worry about it. But what did we see the other day that we have to make a note about? There are only vertical tangents when... Oh, I already gave you that example. That's no fun. Oh, I gave you the answer. I was excited to see if we could figure that one out. Most of you wouldn't have even realized. Anyway. Shouldn't have said anything. What was the note? When f prime of x equals number over 0, to have a, can I call it a VTL? Not the vertical line test, but the vertical tangent line. Is that okay? When f prime of x is equal to a number over 0, to have a VTL, wait a minute, it's not automatic? The one-sided limits of f prime of x I could not think of another way of saying it, but there probably is a better way. When necessitated by the domain. In this one, the domain was only greater than or equal to 0. There was no other side for us to test, so it's sufficient for us just to say, oh, it's a vertical tangent line. There's only one approach anyway. But if you can approach the discontinuity of the derivative from two sides, they must be in agreement. And if they're not in agreement, that's the sharp point, the cusp. Is basically when the limit as x goes from below f prime of x does not equal the limit as x. Let me just make it a instead. When the one-sided limits do not agree, that's when you're going to have a sharp point. When the one-sided limits of the derivative do not agree, which this one as I go towards 0 from below or towards 0 from above, it's not going to work. And that's seen by the original function, f of x equals. The slope on one side is not the slope on the other, so therefore at 0 you have a dne. Because remember, the derivative is defined to be a limit. So if the derivative is not in agreement, the limit does not exist, the derivative does not exist. And the cusp, well, basically it's what the note was talking about. So the cusp is, what if you're coming in towards a sharp point, but you have infinite limits as you come in? This was a constant slope. That was a constant slope, and the constant slopes did not agree. The sharp point cusp will happen if you have some sort of infinite slope as you come in. So this will be when f prime of x also equals number over 0, but the note above fails. Is that a summary from what we saw in homework the other day? I think that's pretty close. So cusps and vertical tangent lines both have infinite derivative. Can I say that? Infinite slopes. Vertical tangent lines will exist if the domain is restricted, so you only can come from one side, or coming from both sides is in agreement, are in agreement, I apologize. Cusp is when the one-sided limits are not in agreement. There we go. Sharp points, vertical tangents, cusps. That would actually be a great thing to add to our 15 identifies. 16 identifies? Would that make it like 19 identifies? That's funny. But we won't do that. Aryan. Yes. Thank you. So you have the concavity, negative infinity, positive infinity, not in agreement. It's a cusp. What was the function that we saw the other day? Was it piecewise? I mean, piecewise could do it, a radical and a radical. I think it was a non-piecewise, though. I think it was like like a 2/3 or a. Do you guys remember that homework? It was like 4 different functions. Some of them were weird with exponential fractions. 2/5? The odd ones were the ones that failed because, well, the ones after you take the derivative that the derivative was odd. So 2/5 would have a derivative of negative 3/5, which could be negative, which could be positive, and that's why, yeah. So like x to the 2/5. The ones that were odd and went to even, those were the ones that did have vertical tangent lines because the power ended up being even, so then it would always be positive. So they were in agreement. Anyway, we're done. So we talked about integrated maths today instead of you guys starting homework, but oh well, go team. Homework. Where does it start? What are the problems that I gave you guys? I showed that a second ago, right? 1 and 9 and 13 to 17. We still have 4 minutes. So here, ready? I'm going to get you guys started. We're in chapter 3. I was going to chapter 2. That was so last week. Okay. Ready? f of x is equal to 1 over x. A is equal to 2. Do I want you to actually do it? Yes, please. Oh, come on. I'm not going to make you do too many. Calm, calm, calm. I want you to do it because that'll give you a deeper understanding of what's going on when you see something with something already plugged in. Oh, that's silly. Number 9 has these whole directions and doesn't even apply. That's lame. Just kidding. Yeah. Huh? Delta x is h. This was the third variation, the one that Isa gave. Aha. See why I had you do this one? Who's that? Uh-huh. Plug in the A, yeah? 1 over A or 1 over 2? What's that one going to be? 1 over 2 plus h. All over h. 0 over 0. Keep going. Ah! Complex fractions. Number 9, use the definition of the general derivative. You're not going to be able to use the specific because it's not asking for specific, it's asking for general. So use the proper definition for that one. And the good news is I really did not give you very many using the definition problems, just as a heads up. Who's already done this one? Justin, go do it on the board. Oh, you did? Eric, did you do it using that formula?
No.
Oh.
It's like, I just know the formulas, it's like so obsolete. Once you know how to derive.
As long as you know how to see it.
Yeah.
But I'm not so sure everyone in here knows how to see it. Got
The
it?
answer is
Yeah, you can see what the answer is.
-1/4.
Yeah, negative.
Yes.
Because what would you have had to do? 0 over 0, keep going. If you had seen this problem, you would have had to realize, oh, it's 1 over x and x is 2, find the derivative. That's kind of hard to see. Maybe it would have been easier just to, and not necessarily. But I need some of you guys to get a better grasp on what this is. You can just take the derivative of 1 over x and plug in 2. In the meantime, well, have some fun simplifying complex fractions. Bye, guys. See you later. Don't worry. 13, 14, 15, 16, 17 are all just looking at graphs. When you get past number 9, you can do everything else using derivative rules. Sound good? All right. Oh, I'm too nice.